Today, the Value Engineering Experts is presenting a throwback video of a famous project done in Calgary in 2008. I'd like to start off by recognizing Brian Isherwood, who passed yesterday, a legend in the GTA community. Interesting enough, on Thursday, I'm going to a 50th anniversary for Isherwood Associates. Of course, the firm today is controlled, and I shouldn't say controlled, but Natter and Sari's built a tremendous team involving monitoring and a lot of young people, and there's been a lot of success with Isherwood. Matt James did the design for the bow video and was very involved, and we self-performed the monitoring. Now, the bow video covers the project for Encana. It was a very expensive building, very well designed. Ledcor was the construction manager, Mike McAletsy. Say hello to Mike. Hopefully he's doing well. HC Macon bid the project, and that bid was $10 million. And Isherwood was our design build partner, and that bow video can play right now.
So what we did is we cut and pasted very quickly. Matt and I are both busy, and we're literally finishing this off about 2 hours ago, as would be typical of one of your designs, Matt. But in any case, we thought we'd come up with a format where we're trying to zero in on what people really want to see at these ventures. There's a lot of engineering talks you go to, and people tend to go over their technical papers, and we wanted to focus a little bit on what we saw was the challenges and the lessons of the job. We wanted to give openly of our knowledge from this project and our thinking behind doing something like this for the benefit of everybody. So we came up with a bit of a tag team. We're going to look at some background, and then Matt's going to cover geology, and then I'm going to talk a little bit about the challenges from a contracting perspective on something like this. Matt's going to talk about design and challenges from a design perspective. We'll look a little bit at site progress, and then we'll look at some specific lessons. There's 2 city blocks in downtown Calgary. One of the key elements was, disrupting 6th Avenue. And that road there is near and dear to the people in Calgary. It's a one-way street, perhaps 4 lanes. It takes the Calgary Stampede Parade every year. So one of the key things was they can't reroute the parade. You would think that they could take this parade and move it over 2 blocks. There's no way they could do that. When the Stampede Parade came up here and went up and they put the horse up the tower every year, then that immediately got demolished. And that had to be rebuilt in a year. So in terms of background, I knew the developer on the project. And it's interesting how things happen in life. But I offered my help to the developer, as a good friend of mine, to evaluate the tenders, in particular the piling tenders, because we had no presence in Alberta at the time. And I said to him, "Oh, I'll help you for nothing." So he thought, "No, I got to pay you." No, I'll help you for nothing. Well, send me the drawings. So he sent me the drawings, and in about a half an hour looking at the soil and looking at the drawings, and the drawings were designed by TerraProbe with a lot of Toronto method, which I knew right away would be a bit alienating to the Alberta contractors, because in Toronto, the market has certain details that perhaps the Alberta contractors are familiar with. Essentially, they were going to do caisson walls next to the buildings and lagged walls away from the buildings. Very traditional design, heavy-duty anchors, long piles, 70-foot deep excavation. So, you know, what causes an inspiration or an idea on design? I'm a big believer in, you know, forces other than myself sometimes in some of these ideas. But, you know, essentially I saw the solution very quickly, that if we could seal off this notorious gravel layer, which is the root cause of many ground loss events on deep excavations in Calgary, a lot of sinkhole activity. And you've got this water layer that runs on top of the rock from the Bull River, and you've got this poorly graded gravel, basically 15-inch boulders minus, no cohesion, reasonably dense. Matt's going to talk a little bit about the soils. So, you know, what do you do pre-tender? I went and met Natter and Sorry from Isherwood, had a lunch with him, had another lunch with him, and then we bid the job. And he thought that the solution was a good one, which was to stack one system on top of the other, to take the secant wall technology, completely seal the gravel off, apply it everywhere, get rid of the ground loss risk, and then in the lower stratums, totally different, the rock, apply a shotcrete solution. So it evolved that way. And, you know, obviously for us, you know, what's the market price? And, you know, you're really guessing at that point. So some quick numbers. You've got the size of the job there. There was, in the end, about 1,600 anchors. And the tower was on the north side of the site. So it's a bowl-shaped tower. At the time, it was going to be the largest building in Western Canada, 58 floors. During construction, it was surpassed by the one building in Vancouver now that towers above the clouds. But certainly it's the largest building, or will be the largest building in Alberta. So some of the advantages to the owner, as it turned out, was that we were able to seal off that water, and what was going to be 900 gallons per minute dewatering was reduced to 10. Like, we literally had 10 at the end of construction. And that would remain the case today. The shotcrete was flexible. We even used it for the Bull Tower slab at the bottom. They literally poured 14,000 cubic meters on that rock in one continuous pour. I think it was the third or fourth largest pour in the world, continuous. Unbelievable what they put into those raft slabs in Calgary. So the shotcrete was flexible. The dewatering was a big benefit. We saved about $3 million over the tendered prices from our competitors. You know, to me, there was additional savings, you know, if they had looked at maybe eliminating the bentonite system they specified. And we could go off on tangents about, I'd love to go off on a tangent with everybody in the room about bentonite systems against shoring systems. But essentially, I believe in sheet draining. And they didn't go for that, but there could have been additional savings, probably 3 to 6 months schedule savings on $1 billion building. So if you do the math on those things, and really no ground loss, which, you know, we're saying is a priceless benefit. Because when you're a developer and you're losing streets to, you know, when these things cave in and you got public safety issues, and anybody who's familiar with Calgary would realize how large that was to have a no ground loss system. And that's what we had to sell to the owner. So now Matt will come up and cover a little bit of geology for the benefit of the geotechs in the room.
Thank you, Martin. So we were very quickly introduced to the Calgary geology. It wasn't something we were familiar with. We hadn't done a structure there in probably 25 years. Brian had done some bridge work there many years ago. But in Calgary, what one sees at this site, fairly level. One of the regions, one of the whole blocks was a parking lot, but 3 to 5 feet of fill. And then it gets interesting because, as Martin had suggested, there was 20 to 25 feet of gravel. And the gravel was really nasty stuff because it had this 15-inch minus, poorly graded, but what Martin didn't mention, it was extremely well rounded. So it literally was just a stack of marbles. And what we came to understand was the approach in Calgary was to simply accept that they were marbles and that they were going to have ground loss. And what they would do is they would put the first level of shoring, they'd step shoring in, and they'd put soldier piles and lagging outside of their site on city property, and then put that down to rock, and then step inside, and then put a whole new shoring system of soldier pile and lagging inside that, conceding that the sidewalk was going to have to be completely replaced, and that during the lagging operation on several occasions they were going to lose meters and meters and meters of these gravel and cobbles that were going to fall into the site in the next lift of lagging. So it was quite strange, and then what they'd do is they'd pull that soldier pile and lagging system out, the upper one, when they were finished the structure, and then completely rebuild the sidewalks. And what this also led to was water that sits on top of the rock here, and that would vary in spring, summer, and winter conditions, but you'd have 1 meter to maybe 2 meters of water sitting on top of the rock. And with this double soldier pile and lagging system, what would happen is the water would come down across that little shelf of soldier pile and lagging and then run down the inside of the rock. And in our rock, that wouldn't be a big issue, but in Calgary rock, it's an enormous issue because it's highly susceptible to weathering. And they called it mudstone. And of course, Martin and I, very early in the project, when the first drill was on site, I got myself up there and Martin was out there. We're kicking off a big project. And we put down that auger and started drilling the first holes and got them in through the gravels, and then looked at that rock. How's it going to drill? And up came till, and we discussed it. I remember sitting over the hole, and this was being described as rock, and our comment was, well, that's awfully generous to call that stuff rock. And one of the nukes, how did he say it? Well, I can't get the accent, but he said back in Newfoundland, we got potting soil that's harder than that. So that's what we were drilling. But what's incredible is that when the water and oxygen hits this stuff, it literally turns back to a very soft clay, so that umpteen problems. And I'm going to go back one slide if I can. There was a site right here that was one of the largest excavation support litigations in Canadian history, maybe second or third, for enormous movements that happened on that site right about here when the building next to it started to move into the hole. And so this is the kind of thing that we were facing when we approached this project. So onto the rock, layered mudstone, siltstone, and sandstone of the Porcupine Hills Foundation. So there'd been a lot of work in this rock. But when we investigated to find out what people really knew about this rock, that's when things started to fall apart. And as we tried to dig deeper into the local lore and soils investigation and geotechnique, we found out that people didn't know a lot about this rock. There hadn't been a lot of studying on it. Very difficult to drill. They basically gave up coring it and went to wash boring and just sort of said, it's mudstone, 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 because there was gut coming out of the hole, and then you hit the siltstone or the sandstones, which are much harder and you could actually core and analyze. So it was an interesting problem for us. So I mentioned that the mudstone's highly susceptible to weathering. And it was very interesting when they talked about the movements, because one of the things that emerged was that the rock had a spotty history of its performance. In some cases, like that case I'd mentioned just kitty-corner to our site, there were very, very high levels of movement in the rock. And yet you could throw a stone from there into other excavations that didn't experience a high amount of movement. So it was very curious what was the driving force of the movement. So we had this problem of trying to design a 75-foot hole that was really large, 142,000 square feet. And what were we going to base our design on, and what parameters were we going to use? So we had this unknown mechanism of movement, and there were suggestions as to what might have been causing that, and they were in the soils report, but they weren't definitive. One of the things was where they talked about high horizontal in situ stresses. And that's something we certainly bump into in Toronto. And when they talked about a K of 2, well, that didn't really frighten us because we see okay, umpteen times that in certain situations in the downtown core. And that had been measured and well documented, and we were starting to understand that. So the other thing they talked about was a weak layer, and this was described as the shear band, or shear band effect. But then when we tried to probe and find out, well, is it a layer of rock that has a very weak moduli? It wasn't known. Was it a layer of rock that had a very low shear strength, internal angle of friction? What was its strain properties? What about strain rate? There were no answers. So it was a very difficult situation to throw ourselves into in an area where we didn't have a lot of experience, and then come up with what the contractor was pushing for a very aggressive design. As you know, the relationship we had with this contractor and many others in the room is that we do tend to become very aggressive with our designs, but aggressive with checks and balances and very good monitoring and this sort of thing. But here we're in unknowns. So this is what I'm talking about. What you see is us looking off towards the east, and that is the police station in Calgary. To the south is a historic structure, the Royal Canadian Legion, and this is at or about 6th Avenue that they tore out. So we have fill materials, we have the gravels, and then we start to get into this mud and siltstone. And here's a nice layer of the limestones, which were very, very strong and sometimes extremely massive, very difficult for the excavator to get through. And then siltstone in between. And here we are in the west wall, and we're well down into the excavation now. We've got the continuous caisson wall over shotcrete, and here we have mudstones, sandstones, and then a thin layer of mudstone in between that might have been water-bearing, another layer of sandstone. And this is one of the interesting formations that we see in there, and it's actually on that photograph right in here. Tom, help me, correct me if I'm wrong, but I believe it's right in this layer. And what we have is a very steep plane within the rock, within the mudstone, and it's actually slick-and-sided. And so what that means is in presence of water, that mudstone turns to a very weak remolded clay. And so we have these situations where we have these very thin beds and often inclined of planes of preferable movement within the rock. But what was really mystifying to us at this stage was that sometimes they produced big movements and sometimes they didn't. And we didn't know why. And we're only starting to really understand that as we do some more work today. The next problem we had was, as we were going to work with this material, how were we going to design with it? We had to come up with rock strengths and other rock properties. And so these were revealed to us over time, but we didn't have all that information at first, but this geotechnical report was guiding us. And so they gave strengths in the mudstones of on the order of 0.1 to 0.8 MPa. In the siltstones, somewhat higher. Sandstones were actually very competent and strong. But then there was this problem of the shear bands. And we didn't know how to handle those. We were given some hints as to how to handle them, but it was really unknown how we were going to incorporate that into the design philosophy. So I'm going to turn it back over to Martin in terms of, we've gone through the geotechnique, but now he was working on the contract and how he's going to carry that forward. And we'll get a little more into the design philosophy after.
Thanks, Matt. So obviously we were, concerned with anything that Isherwood was turning up in the design process, the detailed design process, and all I had to do is remind Nat or the two lunches we had and said, well, you didn't mention it then. But we, as a team, meet the challenges. I wanted to talk about a few of the contractor challenges. So to sell this job after you're low, we got to give confidence to all the stakeholders. We're not a local contractor. I mean, Isherwood is not even known really in that town. So we had to do a number of face-to-face meetings and written presentations relative to questions that people were coming up with. The Isherwood reputation goes a long way. you know, if you have a diligent engineer and they're at arm's length somewhat, then they're very good to sell the alternate. And we rode their horse into the contract. Transparency, I'm a big believer in transparency. I don't hide anything. And, you know, we talked about the benefits and the risks, and even though we didn't know all the risks then, but we were able to identify before everything was signed that the shear band risk should be the owner's risk. That was a key thing to pick up there, because it's very hard to identify this risk, and anything deep in Calgary in the rock is almost an unimaginable risk for someone with a building nearby if that shear band and the inclination is not favorable. Because as we might talk later, Matt found that, you know, you couldn't arrest the movements. I mean, it's impossible to economically anchor that. You're offering an economical anchor design, and the developers realizing a benefit, so the owner and developer together should be sharing or taking the risk of these shear bands. So we talk about the benefits in detail, and the key one to avoid ground loss. The other challenge was to satisfy Isherwood's need for precision monitoring. The standard of monitoring in Toronto is very high, and rightly so, because in the observational method of design, we all want to confirm our assumptions as we go before you're fully exposed with the depth of cut. And the problem with there's no monitoring service in Calgary to compare to the type of firms that are available in Toronto. So along the lines of that, my early thought process was, you know, that the layout of the secant wall was critical, because anytime you have a secant wall that's holding back true water or possible ground loss events, you really want to not have any breaches in the wall. We had 900 piles to put in. So we use a conservative interlock of, let's say, 8 inches and the 35 feet of secant wall we installed. And then we get very precise about the layout. And so we tried to combine and self-perform these things. I came up with a frame system that I could lay out, because I was worried about this gravel and the control of the location of the holes. I really wanted an extra degree of care there. And I think that care, you know, it helped production. It forced a systematic laying out of production, what I called sequences. And I would pre-engineer the sequences with my field engineers, and then we had to do the holes in a certain order in order to optimize the closing sequence. Because when you close the caisson wall, it's a balance between drillability of the concrete and other factors. So I picked a 5 MPa here, and they traditionally were using 1 and 2 MPas. I think really 5 MPa was the right call, because we didn't want to be moved over in the gravel. We had to actually drill boulders. We had to have strong enough rigs that we could drill the rock and break it up and hold these liner systems, which are the Luffer systems, familiar with a lot of contractors and people in Toronto. So field engineering was unusually invested in trying to reduce and enhance our risk, like enhance the QC and reduce the risk. And I think really that's the future of many of these design builds. The contractors have to get more quality control. You know, it's all about the quality control and taking it on in-house, and trying to not be afraid to say this engineer costs this much. I mean, you got 15, 20, 25 men on the site. You'd think we could have 2 or 3 engineers that are logging everything and controlling everything. And to make that pay, I was taking on extra scope, such as the monitoring, which we did in partnership with Monitor. And they would read the data in Toronto, and I had the technicians trained with their help, because it was a bit impractical to pay them to fly in to test things. So we had inclinometers, we had extensometers, which gave very valuable data, and we're not really covering it in the paper, but there is good information about the value of the extensometers to Matthew's confirmation of design assumptions. So the GC concerns, they were challenges. I mean, they felt that because we excluded monitoring, but we were doing a design build, if our engineer wanted this degree of monitoring, then we should pay for it because it was our engineer. And you get into that circular argument, but we ended up, you know, coming to the table on a bit of it and getting the monitoring that Isherwood needed. So the other challenge 3, was resources. I mean, this is a big job. You know, I heard horror stories about not being able to hire labor in Calgary. And, you know, we're a big believer in youth and in teamwork. and you apply that principle, and you know, it turned out well. I went myself onto the site, and I took 2 people from Ontario because I didn't want to maintain my Ontario operation. I didn't want to take equipment and men from Ontario. So everything you see here, we mobilized, bought, and hired for that job. And really the key to any successful job is to mob once and to have a vision of the resources required to get that thing right. What drills do you need? What tooling do you need? We had literally 1 month to mobilize. Fortunately, there was a 5 or 6 week permit delay. So by the end of that time, I was ready. I don't know if I would have been ready in a month. The 4th challenge was, oh, this slipped in here. As the designer's a busy guy. So on those timelines, it's very, very difficult with the degree of man hours that Isherwood had allotted to get the drawings and to get something started. This is actually Matt 2 hours ago, trying to do his slides for this presentation. And there's some of our team, and you can see there's a lot of youthful faces there, but it was a great group of guys, and really teamwork conquers all. And there's a picture, a nice picture with the Calgary Tower there, and there we're doing the sequence 1 of the project, and we're laying out the frames. So it was interesting, they couldn't get permit, and in the 6th Avenue, they wouldn't let us demolish 6th Avenue until after the parade came in. And I said to them, you know, they said, well, how long is it going to take to do the job? And so part of the selling feature was to be a little optimistic. You know, we're going to do it in 8 months. Big job, but it's doable with the kind of hustle that you get out of Toronto contractors. But they'd never seen that kind of production before. And they said, well, how many of these vertical holes are you going to do? And I said, well, we should average about 5 per rig, 5 holes per day per rig. And in this gravel condition, typically they see 1 and 2 holes, and they do triple casing technique, which is an older style. But to take this casing and put the power to it with the torques, you know, I envisaged this production. And within a week, we were achieving that production. And they didn't think we would achieve that. So they had made the commitment that if I was held up on 6th Avenue, they'd pay me for my machines. So needless to say, I was, you know, happy that I got the production. Because once we got over to 6th Avenue, they had to pay me for that delay. Of course, we negotiated a favorable rate, worked with them. There's a picture of the raft slab on the north, and this was all shotcreted to allow them for no backfill condition. That was added in to the contract. And we took pictures from one perch at the Telus Tower. It's about 35 stories, and we sent them to friends and co-workers as the hole advanced. And now you can see the steel just right past the perch. It's quite interesting. This is the largest structural steel contract ever in Canada for a building. Really done at the peak of market conditions in Alberta, like the cladding, the glass on the tower, and the decisions made were a function of a busy market. And today, you know, they've actually had stoppages on that job as they try to organize their financing. So it's amazing how things change. Give it back to Matt.
Thanks, Martin. You saw 1987 up there. It's actually 2007. Of course, I was still in elementary school in 1987. So design philosophy, one of the things, you know, as Martin said, this job was designed on the back of a napkin during lunch by Natter and Martin, and then Natter just handed it over as he can, and, you know, Matt will be exciting, and it's a 1 hour flight for you and 3.5 for me. So, of course, when we got into this, we realized pretty quickly that, you know, conventional design parameters weren't really going to work, so we really tried to avoid those and went into a finite element style of design, and that allowed us a lot more leeway. One, there's very few people who can check it. And two, you know, parameter selection is really left up to the engineer because you can't measure those parameters. And then three, we've got a contractor breathing down our neck. So it really opens up the design possibilities with all kinds of, you know, terrific ramifications. But all kidding aside, we did operate under a non-conventional basis of design, but we had to come up with these parameters in a situation where they really weren't known and the geotechnical information wasn't adequate to allow us to do this. So we had a real issue there that we'll talk about in terms of challenges in just a moment. But what Natter had come up with was and Martin, was a really brilliant design of caisson walls over shotcrete in the rock, because the caisson walls took care of all these traditional problems in the Calgary soils. And we felt we could handle the rock with the shotcrete design. Shotcrete basically was a weatherproofing. And the anchorage for a shotcrete style of design is brilliant because you can change it every lift as you go. If you think you need to, you can put in longer anchors. You can change them, as you know, the gentleman to my right did throughout the project. That's why I'm sitting there with the last 2 hours of doing my design, because of course we do the design and then Martin says, well, I didn't put them there. So we got to redo all the drawings to show him where Martin put them. So the anchors that we used eventually in this design, which was another philosophy that created a lot of argument amongst our team, was the anchors were used eventually in the rock to create a gravity block, if you will. And there's a lot of different philosophy around how to do that. And we differed on that, and actually in its execution and what we ended up with in the end. And we'll show you how that worked. Now, again, we based our design on finite element or finite difference analysis, the FLAC analysis that we had a lot of experience with. And it was very interesting because of our extensive experience in Ontario and the excavation support that we've done here, and the benefit of having, on many occasions, improved geotechnical information that came from the Sheppard Subways, it came from Professor Lowe at the University of Western Ontario and some of the work that he'd done in town. It was extremely beneficial because when they came around and said, well, this is the rock, this is what we think the strength parameters are, this is what we think the K of 2 might be, we ran all the analysis and you just weren't getting the movements. It just wasn't all adding up. And so we knew there were other forces at work, and as a comment to the respect that really is due to the engineers in the room, that when Martin and I stand here and talk to you, I mean, we're actually looking at people who taught us how to do this stuff. And when you look around the room and there's a senior geotechnical engineer that makes some commentary, well, you really have to listen. And this is what was in the report. There was a discussion of the shear band effect and comments about what might be causing it. And when I called up the engineers to find out about this, I never actually got to talk to the senior engineer who'd made the commentary in the report. And it was that the shear band he felt was a discontinuity, basically a slip band in the rock, and this is how it was manifested. And the younger engineers were saying, well, we put that in because he really wanted it in there. And it turns out that that commentary really was revealing in terms of how this whole thing might really work. And the poor man, he'd never made any measurements. He just dug a whole lot of holes in Calgary. So what it came back down to was how we're going to model this rock. And that was a huge challenge, because as we went through the experience we had with FLAC analysis and how the movements were going to look and how they were going to manifest themselves, there's all kinds of different inputs. There's the modeling method, right? We were using finite element or finite difference. The assumptions about that material and how it's going to interact and how it's going to interact with the structure. Rock properties, and not just the simple rock properties, cohesion and that sort of thing, but moduli, Poisson's ratio, interaction effects or discontinuity effects. And then this very interesting one, which is the mechanism for the shear band effect. And I'm going to show you a couple of slides that might help us reveal just a little bit of insight into that. So here's the design that eventuated from this. And so what you see is a caisson wall that was taken down into the rock, and the much debate about how far to take it in. And a good contractor that we were working with insisted that it go down deeper than we even thought it should, because he just wanted to make sure of the problem. So hats off to a contractor who wanted to spend a little more money. And then we had to get down and get this first anchor in, and because in Calgary, you have to remove any anchorage above 7.5 meters of depth. Well, that is in there, and it has to be removed after the project. So what we did is we put a coupler in there so that these anchors are actually de-stressed and unscrewed at this point and removed so that they don't hit the charges. And that's why that first one was left deep, and that's why the second one has a bit of a span there before you lock in the toe. And then I talked about creating a dam effect or a block mechanism with the anchorage in the rock. And that's why you see a number of anchors of the similar length. And what I was arguing for was all anchors of the same length all the way down. And then through our design strategy and discussions, it was decided that we could save a little money if we remove or shorten these lower anchors. And it worked well. And in fact, the contractor insisted that another anchor be added here because he just wanted to make sure of the job. Now here we see something interesting. That's an extensometer. So that is a device, electronic device, that can measure changes in displacement at discrete points along the anchor by being read with an electronic mechanism really out here. So effectively what we were able to measure was the changes in deflection at distances from the face of the wall. And so that really allowed us to analyze just how far back the stress and the movements we're getting in the rock. Great instrument. And then we had inclinometers, and we were very careful to take the inclinometers well below the toes of the piles, and in fact 10 meters below the final excavation of for the building, and that proved to be key. Challenges. So I've mentioned geotechnical parameters. What we wanted to do there was mine the local expertise and talk to all the best geotechnical engineers in Calgary and Alberta to try and find out what we should do with this. And there were some really good people with interesting opinions, but there was no real factual basis for the advice that they were providing us, which was very frustrating. So what we did was we devised an observational method plan. And it had to have wings. We had to make this thing fly because it had to go through the city of Calgary. We had to get this under peer review. We had to come up with something that was workable in the face of all these unknowns. And from that, what we had to do was we had to generate a baseline. We had to figure out just what we thought this excavation was going to do. But that was just the start of all our analysis. We had to figure out what we thought this thing was going to do, and then we had to look at every plausible deviation from that. So we were prepared when we started to dig this hole and the movements told us what the truth actually was. The movement, shape, and magnitudes were going to reveal what the actual rock properties were and how we should have modeled them. And here's just one example of that. This is a displacement contour for one of the models that we ran for a given set of parameters. And what we had done here was model a very weak layer in the rock below the toe of the foundation that had a given thickness and a given reduced moduli in strength. Okay? 40 millimeters of movement, very distinct movement profile at the face. And here's one that shows actually a discontinuity at the same level. And you can see that the movement profile in behind is entirely different, and that this is actually a slip plane. And as we walked through all these different parameters and how we were going to set up the models, we got to see this and how things were behaving and modeled case histories in the Calgary area and tried to match them up with the plausibilities of different soil properties, discontinuity properties, soil moduli, and that sort of thing. And from there, generated a parametric analysis that we were prepared for what kind of movements we actually witnessed, and then we could figure out what was actually happening and how to react to it. Martin?
So we have a section here where we're just going to look at some of the site progress. So this is the vertical drilling of the caisson wall using the Luffer casing systems, our frame layout system, and special augers that can tear apart these boulders in situ. We had some long piles. They had this concept that they had to get out of the ground and erect an umbrella slab. So we ended up getting paid an extra to put in some long piles to take vertical load from this umbrella slab. And there's that Luffer casing system. We did all the tiebacks with 152 millimeter casing systems generally the first tieback was, a little arduous getting through the boulders and then sealing in the rock. A lot of tiebacks are done in Calgary in the gravel. They get great results post-grout in the gravel. I wasn't that confident that I could pull that off on this job, so I went to the rock, which I'm more familiar with, and we had about a 5.5-inch hole in the rock and made sure it was plenty long. One of the things we did is we took on the trimming of the wall. We offered an extra price in our negotiations, said let us trim everything, because really in this kind of work, it's good if you can control the face. So I mobilized rotary cutters on excavators. I wanted to trim that wall, and in particular, I wanted to control that pile toe. I really wanted to be careful with that pile toe. And this is a low vibration tool I used to use years ago on the Seaway, when we used to have to scale the walls, and you couldn't use hole rams. You had to use low vibration. So, this tool really should be used in Toronto. It does a really nice job. But it's all a question of economics and trying to convince an excavator that he should have something like that. There's another picture of, those are Casa Grande M9 tieback rigs. There's a picture of a shotcrete panel between two lengthened piles. We used mirror drain as required because the rock is fractured, and even though we went down into the rock a substantial amount to try and develop rear friction and safety factors, we still had water, spouts. And to make the shotcrete a good job, you really should put some mirror drain on it. We went with a consistent rebar spacing rather than a random rebar spacing, which is often just there to hold the mesh. So the mirror drain has water flows, there's rebar spacing. And then we did a little bit of paneling near the bottom there. And you see the bottom of a soldier pile there. So we started off with berming and conservative measures, and as we got a little more confidence with the monitoring and transitioning this area to a shotcrete system. For instance, we ground with our rotary cutter this area of rock so we could get our shotcrete lapped up over into that area of 5 MPa. And you can see some of the site water, mainly caused by the gravel on the open side of the site, continually pouring water into our site. And the excavator deciding it was best for us to be in the low point, working all the time. It was interesting. We'd given an 8-month schedule to the developer and to Leadcore, and they really thought that we had to meet that schedule. And the first day on the site, I talked to the excavator. He says, well, I told him a year and a half. So I thought that was a bit of a disconnect. A year and a half for him and 8 months for us. We were there over a year, mainly because of the permit delays. So this is looking from that perch down onto that north side. There's that 6th Avenue there. We have quite a number of pictures that evolved this down to the bottom and then ripped through here in a mad rush to try and get that bridge rebuilt. And then by the time the market turned, they didn't know what they wanted to build over here, which was further delay. So you can see the winding excavation coming down, and they're starting to get into breaking the rock, and our operation, getting squeezed onto that south side as the hole advances. And there's the bowl raft slab, and you see that long steel there. They took these steel columns, pumped them with concrete from the bottom, and that was their idea, the umbrella slab. And I can honestly say that that's probably the biggest construction mistake I've ever witnessed on a building of that size, because they had to infill all these floors with concrete work after the fact, but they felt they had to get that tower going. Anyway, there's the 6th Avenue slab just being poured there. They thought they couldn't get form workers, and that was one of the reasons they went with steel below grade. But typically on a tall building, you do at least a few floors of concrete, and everything below grade's concrete. Like, you don't do steel below grade. It was a big economical hit for the developer or the guy who owns the building. And the formwork guy from Vancouver came in, and he just built that like nothing, and they ended up paying his guys to stand around because of the contract that he had. And you see some of the interesting steel structure coming up. 6th Avenue built. We're down on this side. Bit of a tricky ramp removal here. So I'll turn it back to Matt.
Thanks, Martin. So, very important part of this project was the monitoring program. I talked rather cavalierly about how we were treating the design philosophy and using FEA and, guessing at parameters and all that sort of thing. Well, we certainly worked very hard to come up with realistic parameters, but what we really did was we put in one heck of a monitoring program. Precision monitoring of the face of the piles, 12 inclinometers on the project, multiple extensometers, I believe there was 8. So a really heavily monitored excavation that ended up falling on Martin's lap to pay for it all when it was excluded. And partly because the contractors were saying, well, that price is exorbitant, in this project we'd probably have $50,000 worth of monitoring, and our bill for the monitoring was probably $400,000. Well, as I stated, we were looking at implementing the observational method, and that method is let's make our best guess and then monitor it and determine exactly how it was behaving. And some of that analysis you saw was actually reanalysis based on the movements that we were witnessing. And we did that continuously, and we did that on many sections of the site. And our fees were representative of all that work. So this gentleman took on a design build with fees from a design group that were 5 and 6 or more % of the cost of the excavation support system. So this doesn't come cheap. Very heavy consulting fees, very heavy monitoring fees go into this so that you can move forward with such an approach in the unknown. So as I said, we were adjusting things as we went, and most importantly, we were refining the flak analysis as we went down and experiencing the shear band effect. And we witnessed it actually on the northwest corner in the first part of our excavation. And it was significant movements that were happening. Reanalysis, went in, adjusted the anchors, put in more anchors, made all kinds of calculations and an estimation, and then continued to dig and really found out that we couldn't control it. When there was a shear band in effect, the loads were, or the movements really, we weren't able to subside with additional excavation retention systems. It was going to move. And what we really needed to be was prepared for it and make sure that it was going to be of a magnitude and that the effects of it weren't going to be a problem outside of the site. And that's what was really interesting, is that in that area where we saw deep shear band, effectively with the extensometers, we saw that that movement spanned well back from the face of the excavation, over 2 excavation depths from the face of the excavation. And normally, excavation effects are confined well within the depth of the excavation, away from the excavation. So you get a 75-foot deep excavation, you're not going to see effects beyond 50 feet. Well, we were seeing them 150 feet away. And what was really important part of this is as we worked around the site, and we had a real good young geological engineer on site, and we're mapping these shear bands, and we're seeing these shear band structures all the way around the site, but we're seeing shear band effect only in certain areas. And that was very confusing for us. So we mapped these things out, and Tom was on top of it all the way through the project. But we didn't know when it was going to happen. And so what we really wanted to do was figure out how and when and what was driving it. And that drove work that was done on site where we exhumed this rock. When the project was virtually finished, I mean, we were in the last throes of the site, and we went in and found an area of this shear band of material, dug out great whacks of it and sent it off to 2 different laboratories in Canada to have tests done on it. Very extensive tests. They're going to be the topic of CGS articles for some time to come. And that's what drove it, was the monitoring, trying to understand the problem, and then actually having a contractor who was cooperating with us throughout it. So one of the things that we used quite extensively were inclinometers. As I said, we had 12 of them around the site, and there's some very interesting things that came out of that. We had deep inclinometers from ground surface well below final excavation level, well down into the rock. And as we excavated to top of rock, this was a fairly typical inclinometer profile. And so then now as we dig into the rock, we see that the inclinometer's showing us that there's movements down into the rock excavation level and somewhat below. It's an elastic response. And so as we dig deeper, we see that the inclinometer typically moves in, but there's a rigid point down here where we, the elastic effect is subsiding. And there we are approaching final excavation depth. But here we are. You notice that first inclinometer was inclinometer number 5. Well, logically, inclinometer number 4 wasn't far away. Inclinometer number 4 was in the northwest corner. Inclinometer number 5 was a little ways down the north wall. But look what happens on this inclinometer. We're at top of rock, or not, we're not even at top of rock, and we have a nice straight inclinometer. We get just down below top of rock, and in fact, when we hit top of rock, we started to see movement down here. Look, we're in the rock at this elevation, and fully more than 10 meters below, we're seeing significant movements in the rock at a given layer. And look at this, we're not even at excavation depth, and we've got significant movements in this layer. And yet the shape at this point is pretty much the same as the shape in inclinometer number 5. So the rock mass above excavation is moving in a consistent manner, but you've got this huge movement occurring 10, 12, 15 meters below the excavation level. And this is the shear band effect. Significant. More than 50% of the movement we're witnessing is all happening down in this layer that's only less than a meter thick. And yet, this is inclinometer number 4. And at inclinometer number 5, we really didn't witness it. What's driving it? This is a map that Tom devised. And what we're showing here is excavation depth to top of rock to final excavation depth on a time history in days. And this is the movement at the shear band. And you can see that when we hit top of rock, there's very little movement. But as soon as we get into the rock, we've got significant movements happening a depth of 15 to 20 meters below the excavation level. 18 meters below the excavation level, we're seeing significant amounts of movement. So it's really quite phenomenal that you're getting this level of movement 15, 20 millimeters, 10 meters below the excavation level.
So I wanted to talk a little bit about the piling toes, and a lot of people would be wondering about the perch piles and the wisdom of the perch piles, but it was an essential part of trying to spread the dollars out, as Nader said, spending the money in the right place in order to get this secant wall to shut the water off and all the ground loss events that occur in the gravel. Here's a cross-section of the design, and we got an anchor strategically located, about 1 meter below the toe, because we want to lock that mass in there and try and give this a lot of stability. So our C-row anchor is strategically located there, and you see that grinding out of that caisson wall there, which we lapped our shotcrete up, and we were to get some doweling up into that area. So we had some vertical rebar detailed splines here. When we drilled these piles, and we put 3 bags of cement in every hole, because I didn't want to have this loose dirt down here. I wanted to get my auger down and scratch that and mix and enrich the cement in that area. So there was a fair bit of thought put into this, and essentially we looked at berming off this area, doing it in panels until we had confidence, and controlling the face, which is critical in shotcrete work, that you have some control over the face. So what we're talking about is a perch pile versus traditional methods, where we start to get a discussion about the role of the soldier piles versus the anchors on the job. And as I learned from Matt and as we learned on this job, it's all about the anchors more so than the pile. The role of the toe, we're getting typically a level of bracing out of a toe, and we're getting some vertical capacity out of the toe. So when you eliminate a pile toe below your plunge line, base of excavation, you have to be very careful with the friction in this area here. And ideally, you got a progressively harder soil as you transition into this. But one of the reasons I wanted to get that 3 meters of weathered rock there was to ensure that on my B-row anchor, when I locked that anchor in, that this worked on friction and not necessarily on end bearing. Because the modulus of friction is higher than the modulus of end bearing there. So really you want friction on that. So if we look at a traditional soldier pile, you might be 3 to 5 meters below the plunge line. Traditional pile. But if we look at the example, let's say from Vancouver, and we do a lot of shotcrete relative to our volume of work in Toronto, we're known for shotcrete. Well, there is no pile or pile toe on a soil nail wall. So can you combine the two of them in some conditions? No toe. So in our situation here, you use the pile to get some of your anchors below that 7 meter removal line and the secant wall to completely seal off the water and gravel problem, ground loss problem, get the toe down, lock it in with a B row anchor, put a C row anchor strategically to protect that toe rock there. And that's more or less how we did it. And we wouldn't get any more than, I would think, maybe 5 millimeters of vertical movement on that pile during construction, because we were able to keep that friction. And huge friction values on this area here, provided you didn't have too extensive a use of mirror drain. I mean, we were strategic in how we used the mirror drain and where we drilled our anchors, because you need the anchors to be away from the mirror drain. So you had to move your anchors a little bit so you weren't drilling in a water-bearing zone. Again, you want to avoid services, so the pile is useful, but why can't you then transition to the soil nail design? And the design on the bow is really motivated by the soil layers having different properties. So this idea that you could stack one system on top of another for a cut of this type, I think will be used in the future with some care. Certainly by our company, we're cautious about this type of thing. So lesson 3, which is wrapping up near the end of our presentation. I suggested to Matt that we talk a little bit about being careful with innovation. And I think Matt can close off a little bit with any warnings he would give. I mean, it's not really, it's precedent setting, but it's really not something that you want all the contractors to bid on, because they have to be careful. There's a lot of quality control that you have to have. I don't think we'll see designs like this at the time of base tender, but we are in a design build industry, and hopefully, one of the better contractors can benefit from what we did, and if they see it, they can provide value to the client. So Matt, I'll let you close off.
Thanks, Martin. Yeah, innovation with care, I think that's a great summary of what was conducted here in terms of rolling out the observational method in a market that there was an absence of good geotechnical information on and past experience. We're able to roll that out with the belt and suspenders approach by having a extensive monitoring program that we had a lot of confidence in, and a contractor that we knew was willing to react when it was time and prove that they could react. One of the things that we didn't talk about was that, the filler piles, which are often talked or just there to be in between the soldier piles and provide very little positive effect, our contractor decided that it wasn't terribly expensive for him to take those an extra 2 meters deeper into that rock to increase the amount of friction that caisson wall was afforded. We didn't ask him to do that. He made a decision that it was cost effective for him to embrace greater factor of safety on that upper wall, because we were in a new situation. Similar for that lowest anchor. I didn't think it was necessary, but our contractor wanted to make sure that that there weren't any problems there. So it's not often you get a contractor that's going to do extra work at his own cost to make sure that things are safer, and that was well reflected on this project. And he was willing to pay the fees for additional engineering well beyond the scope and fight with the GC to put in the monitoring that we were asking for. And it was a fight. This GC thought we were ludicrous in spending this kind of money on monitoring. But without that monitoring, we'd have been in the dark and making uneducated decisions. we were able to make educated decisions throughout this project. And I think that was a big part of the success. That maintained profitability for the contractor and enabled us to sleep well at night. So thank you.
The commercial aspects of not only the 1982 working bridge over the Bow River, where the value engineering was reduced silt, because you can't, in the active river, you have to be careful. You know, there's a lot of concern about the fish. We had to support the formwork and minimize the impact of putting the piers in down to that sedimentary shale through that Bow River gravel. That's a layer that runs through downtown Calgary. It's famous, been many problems. And I think Matt James does a very good job in the actual Bow video describing some of the problems. You know, we bid that job at 10 million. North American was at 17.5 million. So big savings going in. That's the nature of value engineering. They tend to be home run savings. And I'm showing it today with our FEH2O lock, which can replace the situation in Toronto that's going to save people $8 million, a lot of schedule time, because when you lower CO2, you save costs and schedule. And that's mainly in the rebar and concrete equations. So in 1982, we did a job with Bill Lardner, Alan McNabb. Bill's passed away now. He was a longtime associate, changed the industry with Brian Ishwood. Rest in peace to both those gentlemen. Alan McNabb's alive today. Stevenson was the general contractor in 1982. So that job, I don't know if I wasn't party to the financial aspects, but it was probably $500,000. And we bought scrap steel, assembled trusses on both banks of the Bow River. It was at a long stretch on 4th Avenue. And that bridge, of course, is well-traveled, curved over to the airport, kind of goes over to the airport. It's a main downtown exit to the airport. In any case, Calgary's a great city. We talked a little bit about the challenges on the Bow with the nature of the 6th Avenue, and you've heard all that. Thanks very much.